black holes could indeed be the key to understanding a quantum concept of gravity and a deeper understanding of how space and time work. These astronomical objects are fascinating because they feature a region known as the event horizon, where the laws of physics as we understand them seem to hold sway. However, at the same time, they present a fundamental conflict between the two foundational theories of nature, quantum theory and general relativity. The quest to unify these two great pillars of 20th and 21st century physics into what is often called a quantum theory of gravity is considered the holy grail for theoretical physicists. In this sense, black holes are pushing us toward a deeper comprehension of the nature of space and time, and it is fair to say that they are indeed keys to understanding the universe. My name is Brian Cox, and I am a professor of particle physics at the University of Manchester and the Royal Society Professor for Public Engagement in Science. Among other things, I am the author of the book Black Holes, The Key to Understanding the Universe. The concept of black holes dates back to the late 18th century, specifically the 1780s and 1790s. At that time, physicists, mathematicians, and natural philosophers like Jean Michel and Pierre-Simon Laplace independently developed the idea of escape velocity. The escape velocity is the speed needed to break free from the gravitational pull of an object, such as a planet or star. For instance, the escape velocity from the Earth's surface is around 8 miles per second. For a more massive object like the Sun, it is approximately 400 miles per second. Michel and Laplace pondered the possibility of stars so massive that their escape velocity would exceed the speed of light, rendering them invisible. This conceptual leap led to the idea of black holes. To understand why black holes present so many conceptual challenges, it is helpful to briefly describe what a black hole looks like. From the outside, a black hole is surrounded by an event horizon, which marks the boundary between the exterior universe and the black hole's interior. If you cross this boundary, even if you travel at the speed of light, you cannot escape the gravitational pull of the black hole. Another intriguing description of the event horizon, derived from Einstein's theory of relativity, suggests that from an external perspective, it is a region where time stops. This notion has puzzled scientists throughout the history of black hole research. At the core of a black hole lies the singularity, often imagined as an infinitely dense point where the massive star collapses. However, this concept is not entirely accurate. In general relativity, a detailed map of a black hole, known as a Penrose diagram, after Roger Penrose, reveals that space and time are so distorted that their roles effectively switch. The singularity is not a point in space but a moment in time, the end of time. For many years, the nature of the singularity remained a mystery, as scientists lacked the conceptual tools to explore it. The significant breakthrough in black hole research came with Stephen Hawking's discovery of Hawking radiation. In a landmark series of papers, Hawking showed that when considering quantum theory in the vicinity of a black hole's event horizon, black holes emit particles and have a temperature. This revelation, which emerged from Einstein's geometric description of distorted space and time, fundamentally altered our understanding of black holes. Hawking's idea involved pairs of entangled particles near the event horizon, with one particle escaping into the universe while the other fell into the black hole, effectively reducing the black hole's mass over time. This process suggested that black holes are not eternal prisons. They have a finite lifetime and eventually disappear. The discovery of Hawking radiation raised a critical question. What happens to the information contained within the matter that falls into a black hole? According to quantum mechanics and general relativity, information should be conserved in the universe. This apparent contradiction, known as the black hole information paradox, challenged physicists to reconsider their understanding of black holes. Fast forward to the present, ongoing research suggests that black holes do not erase information from the universe. It is now believed that all the radiation emitted by a black hole throughout its lifetime contains information about everything that fell into it. In principle, if we could collect all that radiation, we could reconstruct the history of the black hole. This insight has profound implications for our understanding of gravity and the nature of space and time. One emerging view, known as emergent spacetime, posits that space and time are not fundamental but arise from quantum entanglement or some other underlying elements. Although we do not yet fully understand the nature of these elements, this perspective hints at a deeper underlying theory from which space and time emerge. a quantum theory of gravity. To explore the origins of the universe and questions like whether the universe had a beginning in time, we must first understand the nature of space and time. Black holes, observable objects that exist in nature, drive us to ask well-defined questions about the nature of space and time. Einstein once said that if we examine nature closely and persistently, we might catch a glimpse of something deeply hidden, the underlying structure of reality itself. While the ultimate nature of this deeper structure remains uncertain, the pursuit of understanding black holes continues to provide invaluable insights into the fundamental workings of the universe. The research into black holes and the quest for a quantum theory of gravity are ongoing, but the journey promises to reveal profound truths about the nature of reality. For those interested in diving deeper into these topics, becoming a member of a community dedicated to exploring such questions can provide further opportunities for learning and engagement. The journey to understand black holes and their implications for the nature of the universe is a continuously evolving field. As researchers delve deeper into the mysteries of these cosmic entities, new discoveries and theories emerge, furthering our comprehension of the universe's fundamental laws. One such area of research is the nature of the singularity at the center of black holes. While general relativity predicts a singularity, a point of infinite density and zero volume, this notion remains problematic because it suggests a breakdown of the laws of physics as we currently understand them. In recent years, various approaches have been proposed to resolve the singularity issue. Some physicists suggest that quantum effects, which become significant at extremely small scales, might prevent the formation of a true singularity. Instead, there could be a region where quantum gravity effects dominate, smoothing out the singularity and providing a more coherent picture of what happens at the core of a black hole. This leads to the possibility of a theory of quantum gravity, which would reconcile general relativity with quantum mechanics. String theory and loop quantum gravity are two of the most prominent candidates for a theory of quantum gravity. String theory posits that the fundamental constituents of the universe are not point particles but rather one-dimensional strings that vibrate at different frequencies. These vibrations give rise to the various particles and forces observed in nature. In the context of black holes, string theory suggests that the singularity could be replaced by a highly curved region of spacetime where strings interact in complex ways. Loop quantum gravity, on the other hand, focuses on the quantization of spacetime itself, proposing that space is composed of discrete units or loops that form a fine-grained structure at the smallest scales. Both approaches offer intriguing insights but also face significant challenges and remain subjects of intense research. The study of black holes continues to provide a fertile testing ground for these theories. Observations of black hole mergers, as detected by gravitational wave observatories like LIGO and Virgo, offer empirical data that can help refine our theoretical models. These observations not only confirm the existence of black holes, but also provide information about their properties, such as mass, spin, and the dynamics of their interactions. Another fascinating aspect of black hole research is the connection between black holes and information theory. The black hole information paradox, highlighted by Hawking's discovery of black hole radiation, suggests that information about matter falling into a black hole might be encoded in the radiation it emits. This idea aligns with the holographic principle, which proposes that all the information contained within a volume of space can be represented as a theory on the boundary of that space. In the context of black holes, this means that the information about the interior of the black hole could be encoded on its event horizon. The holographic principle has profound implications for our understanding of the universe. It suggests that the three-dimensional world we perceive might be a projection of information encoded on a distant two-dimensional surface. This radical idea challenges our intuitive notions of space and time and points towards a deeper, more fundamental description of reality. Furthermore, recent developments in the study of black hole thermodynamics and quantum entanglement have provided additional insights into the nature of spacetime. The interplay between quantum entanglement and the geometry of spacetime suggests that spacetime itself might emerge from the entanglement of quantum states. This concept, known as ER equals EPR after physicists Einstein and Rosen and Einstein, Podolsky, and Rosen, posits that the creation of a wormhole Einstein-Rosen bridge between two black holes is equivalent to the entanglement of their quantum states. The implications of these ideas extend beyond black holes to the very foundation of cosmology and our understanding of the universe's origins. If spacetime is emergent and not fundamental, then the initial conditions of the universe, including the Big Bang, might be understood in terms of a more profound quantum gravitational framework. This could potentially answer questions about what preceded the Big Bang, the nature of time, and whether the universe had a beginning or if it exists in some form of eternal cyclicity. The pursuit of a quantum theory of gravity is not just an academic exercise. It has the potential to revolutionize our understanding of the cosmos and our place within it. Black holes, with their extreme conditions and paradoxical properties, serve as natural laboratories for testing these revolutionary ideas. As we continue to study them, we are likely to uncover even more surprising and transformative insights into the nature of reality. In conclusion, black holes are indeed pivotal to our quest to understand the universe. They challenge our current theories and drive the development of new concepts in physics. From the resolution of the singularity problem and the unification of general relativity and quantum mechanics, to the implications of the holographic principle and the nature of spacetime, black holes push the boundaries of our knowledge. As research progresses, we can expect to gain deeper insights into the fundamental structure of reality, bringing us closer to understanding the true nature of the universe. The study of black holes, therefore, remains one of the most exciting and profound fields in modern science.